Recording. Okay. Welcome everyone. Thanks for joining us today for the third ECSPrecip seminar of the year 2024. I'm Yoonjin Lee. I'm the chair of ECSPrecip subcommittee. Before we get started, I just wanted to briefly introduce ECSPrecip. We are one of the subcommittees of AGU Precipitation Technical Committee, and our main goal is to provide useful information to students and early career scientists in the precipitation field. We advertise precipitation-related conferences or related papers, and we try to become a bridge between students and early career scientists in the field. So this seminar is part of our main efforts. We've held this quarterly seminar series every year. Today's seminar is the third one of the 2024, and I'm sure this one is going to be really interesting, especially for students, because we invited three experts who are working on investigating various precipitation types. And lastly, I wanted to advertise our last seminar, which will be a town hall during AGU. You'll get to hear various work experiences from scientists in different career stages. So if you're attending AGU, please join us. And if you want to hear more from us, please join our mailing list or follow us on social media. So now I'll hand this over to Lindsay and Aaron, who are the two moderators of the seminar. So enjoy.
Thanks, Eugene. So I guess go ahead and get started. Holly Mallinson is up first, so if you want to go ahead and share. Dr. Holly Mallinson is a NASA postdoctoral program fellow at the NASA Goddard Space Flight Center in Greenbelt, Maryland. Her research focuses on better understanding the interactions between convective storm dynamics and microphysics using a combination of data from field campaigns and high-resolution numerical models. She previously received a bachelor's from University of Louisiana Monroe and a master's and PhD from the University of Illinois Urbana-Champaign, where her dissertation focused on how anthropogenic climate change may influence hail processes and subsequent surface hailfall. Outside of research, she served as an inaugural chair for the AMS Board on Student Affairs and the Board of Representation, Accessibility, Inclusion, and Diversity. Holly, whenever you're ready, go ahead and take it away.
Awesome, thank you. So I'm going to be giving an overview of hail science and research. So to start off with just defining what is hail. So it's defined as ice that falls from a thunderstorm exceeding a 0.5 centimeter in diameter, and it can have either regular or irregular shapes. And hailstones can end up ranging anywhere from 0.5 centimeter diameter to over 18 centimeters in diameter. And the record US hailstone is actually over 20 centimeters in diameter. So you can see throughout these pictures that it comes in a variety of shapes and sizes, some more spherical, some with these protrusions and lobes. And it's really important to understand hail processes and understand better prediction because hail, despite its rarity, can cause billions of dollars worth of damage for property and agriculture. And so getting into hail formation and processes, very general to start. In order to have hail, you need to have convective storms. And so hail generally needs an updraft of 15 meters per second or stronger. It's going to ingest a hail embryo, which is going to collect supercooled liquid water between about -10 Celsius, -30 Celsius is kind of this prime hail growth zone. It's going to collect supercooled liquid water and grow. And then once the terminal velocity of that hailstone exceeds the updraft speed, it is going to fall out of the storm. And so that's kind of the very basic hail processes. Going a little bit more in depth now into the different kind of microphysics of hail growth. And hail tends to be fairly complicated because it can be influenced by warm rain processes, ice processes, and there's a strong kind of dynamics component as well. So we're going to break this down, and we'll start with embryo formation and transport. And when we talk about a hail embryo, what we're talking about is just the center point of a hailstone, the starting point for hail growth. And so hail embryos come in two primary types. You have a frozen raindrop or graupel. Both embryo types have been observed from the same storms, and there's no noted relation between ultimate hail size and embryo type. And we mentioned that hailstones tend to form in these stronger updrafts, but because embryos are so small, their kind of fall velocity or terminal velocity is about 1 meter per second. And so they form in different environments that hailstones form in, and then they kind of just get ingested into these stronger parts of storms and are able to grow. An important thing for embryos also is it's possible that if you have a high concentration of embryos within these kind of prime hail growth conditions, you could increase the competition for super cold water and end up limiting growth. And that kind of served as the basis for some early hail suppression cloud seeding experiments. And so once we have the hail embryo, again, either a frozen drop or a droplet particle, we move into kind of the hail growth stage. And again, hail grows by collecting super cooled water, again, generally between -10, -30 degrees Celsius. As that liquid water freezes on this hail surface, it's going to release latent heat. And then there are two different growth regimes for hail, generally a wet growth regime and a dry growth regime. And a wet growth regime is when the liquid water is being collected sufficiently quick enough that the hailstone surface is going to warm to about 0 degrees Celsius. And so the water stays liquid and able to kind of spread into these porous regions. And on the figure on the right, you can see that's kind of the more clear rings in there. And then there's also dry hail growth, where the hailstone surface stays below freezing because it's collecting liquid water more slowly, and the hail freezes on contact and kind of traps these air bubbles, which is kind of this more cloudy white layer. And the different growth regimes have implications for hailstone density and therefore fall velocity. And you can see that it's possible for hailstones to kind of encounter both regimes. In this one, it kind of cycles between them a little bit as well, or they could just encounter one growth regime. And then as long as the hailstone is able to stay in the storm in these prime growth conditions, it's going to keep growing larger. But as it grows larger, it's going to need a stronger updraft in order to support future growth. And so as our hailstone grows, it's going to continue growing until its terminal velocity is going to exceed that of the updraft. And then it is going to fall and begin to melt. And the amount of hail melt is going to be determined by the depth of the melting layer, as well as the hailstone's terminal velocity. So a large hailstone that has a high, really heavy, is going to fall a lot quicker, and it's not going to be as susceptible to melting. As the hailstone surface reaches 0 degrees Celsius, it's also going to begin shedding raindrops. And this can also happen during the wet growth regime when the hailstone surface stays kind of warm. And this shedding could impact the number of hail embryos, as well as the raindrop size distribution, although this is fairly difficult to quantify, and we don't have great estimates of that currently. And then as we've seen, hail can come in a really wide variety of irregular shapes and sizes, and this can make it difficult to characterize the shedding, which can be enhanced from tumbling as the hail falls. And so that kind of spans all of the microphysics portion of kind of the life cycle of hail. And then when we talk about hail and wanting to learn about how we get large hail, optimal hail growth as it is, that's going to be a little bit more dependent on a balance between microphysics and dynamics. And so we've mentioned a couple of these already, but you need sufficient supercooled water in the hail growth zone, generally between 1 and 5 grams per meter cubed, in order to facilitate large hail growth. You need balance of embryos to not have too much competition. And then again, you need to kind of start the embryo or hailstone in a weaker updraft. And then as the hailstone grows, move into a stronger and stronger updraft to kind of keep it suspended in the growth region. And these last two have a little bit more connection to storm dynamics, as well as environmental parameters such as CAPE, vertical wind shear, things like that. And so talking about hail, because it's really fairly rare hydrometeor, and how we're able to make observations with hail and study hail. Field campaigns are a great way to do this, so I'm going to highlight a couple of field campaigns for that note. So one of them that I got to be involved in is Hailstone. This took place over 5 years, a couple weeks each year, to collect high-resolution hail observations, mostly aimed at assessing National Weather Service hail size forecast. So you can see on the left traditional storm reports, and on the right was hailstone. And one thing about this campaign is they outfitted cars with these metal overhangs so that they could go into the hail core and observe the hail before any melting effects were able to take place, to try and get as close to the accurate size when it fell as possible. Another one is the NASA IFEX campaign, which focused on mapping 40 structures of deep convective storms with a variety of ground-based radars, airborne radars, and other ground instruments like rain disdrometers and things. Here's the Relampago campaign, which took place over central Argentina. This region is kind of a known hotspot for deep convective storms, and there's more of a focus on how terrain can impact severe convective storms and hazards. So there's mobile radars for that, hail pads, different surface stations, things like that. And then this one is Ice Chip. This is actually planned for next summer. It's a focus on hail, and there's, in addition to kind of mobile radars, which have been used, it seems like there's going to be some kind of new ways of looking at hail using drone imagery, some high-speed videography. So it's going to be really cool and interesting to see what comes out of that campaign. And then another way that we can work to understand hail is through numerical models. And I'm not touching on like numerical weather prediction models. I'm talking more modeling in a research sense. So one way to do that is the weather research and forecasting model, which has a WRF predicted hail class. This is more directed at getting a background hail concentration. So it's not going to predict the rarest or largest hailstones, because you need to have one hailstone in kind of a 160 square meter area to kind of be considered the largest for that. But you can pair this with the hailcast model, which is this one-dimensional growth model. It kind of uses some idealized assumptions in order to get like a theoretical maximum hail size that a storm would produce at that time. So the hailcast model in tandem with the WRF predicted hail can be a really kind of good coupling there. And then another method is using CM1 or Cloud Model 1, which is more of an idealized model. There's been an uptick recently of groups that have been using trajectory models and incorporating trajectory models to try and get a better idea of hail processes and understanding there. And so I'm going to highlight a couple avenues of research in hail science right now and see where we might be able to improve things in the field. One area is relating the large-scale environment to hail size. So there's been limited success in predicting hail severity and hail size from environmental parameters alone. Even with some more recent machine learning techniques, there's still some kind of limited success there. You can see from the figure, there's two different metrics for CAPE or instability with bins by hail size, and you can see there's tons of overlap. So just looking at things like instability or wind shear, you're not able to get a great idea of what the hail size might be. And some idealized trajectory size have looked at it. It really is dependent more upon a balance of CAPE or vertical wind shear, mid-level moistures, and things like that, as opposed to just a single parameter kind of maxing out. Another area that could always use improvement is remote sensing retrievals, especially with regards to hail. There's usually difficulties related to attenuation. And these are at the frequencies that are more common for mobile ground-based radars, airborne radars, and satellites. Because hail gets so large, it usually starts to get into the Mie scattering regime where you're not able to get a nice, kind of relationship with particle size. But advances using like dual polarization data, combining data between ground-based or satellite, using different sources can really improve retrieval. So for instance, there's field campaigns that have different airborne high altitude radars on aircraft. Then you can combine that with the in situ data on microphysics planes that are going in the cloud compared to different wavelength radars on the ground and kind of try and get the most complete picture you can from a storm. And then through retrievals, you can construct different climatologies, answer science questions, looking at convective processes, things like that. Another area of research is trying to improve numerical models. So numerical models use rate equations. So things like the rate of rhyming, the rate of evaporation, things like that. We're not able to observe process rates though. What we can observe is the cloud and precipitation properties that are a result of those processes. And so usually we can only kind of indirectly compare numerical models with observations, right? So as an example, we can observe the condensational growth rate of how rain worked. But we can observe the rain drop size distribution and how much rain fell, and then compare that with the model and kind of try and back out processes and what might be going on there. One way to kind of improve on this is something I'm doing here at NASA. There's this Polaris, which is a radar retrieval simulator. There's also different like satellite simulators, for instance, but it uses cloud resolving models and will generate polarimetric radar observables, so like reflectivity, ZDR, things like that. And so you're able to try and do a more straightforward comparison between observations and models compared to just maybe comparing like differences in rainfall, things like that. And then one more area to look at is how climate change might affect hailfall. So a lot of studies have looked at how severe convective storms might change and then extrapolate this to hazards. Currently, there's a lot of uncertainty with how hail may change, mostly as a result because future environments tend to have higher CAPE or instability, which generally means stronger storms that can support larger hail. But future environments also have a higher melting level. And so there's kind of discrepancy on if the higher melting level is going to compensate for the higher CAPE, or if one's going to kind of beat out the other, so to speak. But these studies have largely been driven by how environments are expected to change. And again, environments aren't necessarily the best predictor for specific hazards. And so part of my PhD work was looking into a more process-based approach to how hail might change due to climate change. And so we looked at cold season events and warm season hail events. Looked at hail both at the surface that you can see on the bottom and hail aloft. And the black line is the historic simulations. The different colors are just different climate projections. And we were able to see that there are differences in how hail changes in the future, and it's driven by some seasonal changes. But these weren't explained by environmental differences. So for instance, you can see that the hail aloft is following the same pattern of the hail at the surface. So it's not necessarily that there's larger hail in the future, but it's just melting more. So again, we did kind of a process-based approach for this. And going back to some of the things we looked at, like super cooled liquid water, graupel concentrations, we were able to see that in warm season storms where we had smaller hail, there's less supercooled water in future storms. Again, these different colored lines compared to the black line, as well as more graupel particles for potential hail embryos. And so there's really kind of a microphysical influence on how hail might change in the future. But again, tying back to how the environment can influence this is still an open area for research. And so with that, I'll kind of leave this summary up, and I look forward to any questions. Thank you.
Thank you, Holly. So as I've said in the chat, we're going to be having a Q&A session for everyone at the end. So if you wouldn't mind swapping over, we're going to have Kaidi Peng start to share her slides, and I will give her an introduction. If you guys are anything like me and want to write down what your question is now, please go ahead and do so and drop that in the chat, and we will make sure to prioritize and have that ready when we are ready for questions. So it is my distinct pleasure to introduce Kaidi Peng. She is a third-year PhD student, soon to be candidate in the Department of Civil and Environmental Engineering here at the University of Wisconsin-Madison. I'm in her research group, and she's amazing. She's co-advised by Professor Daniel Wright and Dr. Yagmar Durin, and she focuses on satellite precipitation uncertainty quantification and its associated effects on hydrologic predictions. Her goal is to be able to convert this precipitation uncertainty into decision-making information for flood and other water-related disaster warnings. To accomplish this, she leverages satellite products, physical and statistical models to solve real-world problems, especially in gauge-limited areas. She is also a rock star, as she has just been recently awarded a NASA Finest Award, as well as an A.G. Horton grant for her work. So she is an up-and-coming star. Without further ado, I'll hand it over to Kaidi.
Okay, hello everyone. Now we are going to look at the rainfall process. So before I get started, I would like to introduce where I'm from. So we are the Hydroclimate Extremes Research Group led by my PR, Professor Daniel Wright. We study the measurement, modeling, and analysis of extreme rainfall at high resolution from different data sources, trying to understand how the land surface climate will change the extreme rainfall and associated flood risk analysis. Okay, now we are going to first introduce some background about the rainfall process. First of all, the lifetime of a raindrop. Moist and warm air is lifted and cooled so that condensation occurs at a high elevation due to the cooler temperature. Droplet generates and grows in the cloud. Once big enough, it rains or it falls and leaves the cloud base and starts to evaporate. These droplets that survive from evaporation will contribute to the surface precipitation. There is a statistical relationship between the rain rate and the raindrop size. A larger size is likely to generate a heavier rainfall. A small model is usually assume an exponential distribution of the raindrop size. So you can see, as I show in the equation, from this kind of equation, we can calculate the total liquid water content in the raindrop. By knowing the falling velocity of the raindrop, it will determine how quickly the land is receiving water, which is the precipitation rate. The simplest way to measure rainfall is the rain gauge, which can be a container open to the atmosphere that records the quantity of the water it collects. It's a point-scale measurement. Rain gauges are not evenly distributed over the globe and cannot get high-resolution spatial maps. The other way is to use radar. Radar sends out a microwave pulse and senses the return signal. A larger particle in the atmosphere will significantly scatter its radiation. In practice, we can model a power law between the rainfall rate and this backscattering magnitude. The stronger signal means a higher rain rate. Radar can detect rainfall within a range such as 200 kilometers with a spatial resolution of about 1 kilometer. A local map, as you can see here, can be generated from radar. But its quality will reduce with increasing measurement distance, as shown in its radar quality index. As you can see, that a couple of regions don't have a good quality due to distance or due to the ground cluster. If this radar is mounted on the satellite, then we come to the field of satellite-based precipitation measurement. So what I'm showing here is a satellite from Global Precipitation Measurement Mission. This satellite is equipped with a KUK band radar. However, for most of satellites that running in the space, they can only sense the microwave radiation or the infrared radiation emitted from the atmosphere and from the ground. And the emission from the ground will contaminate the signal from the cloud. So the radar typically has a better retrieval accuracy compared to the pulsar microwave and the infrared sensor. So with the satellite constellation, including radars, radiometers, infrared sensor, we can observe the rainfall and its spatial temporal variability at a global scale. For example, what I'm showing here in the finger is the integrated multi-satellite retrievers for GPM. It's a satellite precipitation product created by an international network of satellites from GPM. There are a couple of different reasons for rainfall. For example, the colder and warmer air must come together and generate a frontal precipitation, a tropical cyclone with a rapidly rotating storm system. Thermal convection due to heated land surface, vertical uplift of air masses due to the topography. So it's also known as the orographic rainfall. And also atmospheric river, which transport a huge amount of water vapor from the accurate to the other areas. It's a different rainfall mechanism, the spatial temporal variation, and the indirect measurement from the satellite pose a challenge on the satellite rainfall retrieval accuracy and also its uncertainty estimation. So that's where my research lies in. What we're showing here is a simple example of the both overestimating and estimating showing in image as I marked in this area. Also, if we look at the cumulative rainfall, the satellite estimate this image is also far away from the ground-based measurement, which is from radar. More importantly, the rainfall error will propagate through the hydrological models, interacts with hydrological modeling uncertainty, and thus lead to biased hydrological prediction. Flood is one of the water-related disasters that are considerably affected by rainfall uncertainty. However, current global hydrological modeling framework doesn't have sufficient consideration of precipitation uncertainty. So based on this research gap, the objective of my study is to quantify satellite precipitation uncertainty globally and to evaluate the influence of satellite rainfall uncertainty on stream flow prediction. So now we try to estimate the rainfall uncertainty in a statistical way. Since we already seen that the highly non-stationary of the rainfall field and the uncertainty in almost all types of measurement methods. So what we did here is to fit a condition distribution given the observed satellite rainfall. However, what's really needed in the hydrological model is a specific rainfall quantities. So we further do a sampling from the fitted distribution to get the rainfall quantities. The outcome of the method is a ensemble precipitation data set called stream set. Ensemble means that for one observed event, we will have multiple realizations, and the ensemble spread is expected to capture the real event. The ensemble distribution will provide the probability of the event occurrence. Okay, now I'm going to dig into the first step of this method, which is to fit a conditional distribution. So actually, it's essentially a nonlinear generalized regression. The distribution we chose here is a sensor-shaped gamma distribution. It's identified by the couple of parameters, mu, sigma, delta. So in our case, this mu, sigma, delta will be determined by the rainfall rate that is observed by the satellite. So if we have different rainfall rate for one pixel, then this mu, sigma, delta will be different. Then a different gamma distribution will be fitted. For example, it's two things here show the different gamma distribution. So it's blue line and the red line. Then essentially can be think as the two pixels that have two different rainfall rate and finally have two different gamma distribution to represent the real precipitation rate. So this conditional fitting, this conditional distribution generally provides the real rainfall distribution conditioned on the satellite observations. So as I mentioned, what we actually need is a specific rainfall value. So that's why the second steps comes to make a spatial temporal allocated sampling. So because we know that rainfall field itself is spatial temporal autocorrelated, so we need to replicate that spatial temporal autocorrelation into our new generated rainfall field. For the spatial autocorrelation, we use the shallow space Fourier transform. Oops. Okay. So the shallow space Fourier transform will estimate the spatial autocorrelation function, which will be passed to the Gaussian noise via convolution. Thus, a set of autocorrelated Gaussian noise are generated. For the temporal autocorrelation, we use the first-order autoregression model. So the correlation between two consecutive time steps in the observation will be preserved in the Gaussian noise between two nearby time steps. Okay, so in the second step, we generate the Gaussian noise that is both spatial and temporally autocorrelated. And this noise will be used to sample from the fitted gamma distribution to get what we call here the stream set precipitation ensembles. So here we put the satellite precipitation. This is three different gradient precipitation, including satellite precipitation, our ensemble, and also the high-quality ground-based precipitation into the hydrological models to investigate the influence of the rainfall uncertainty on the stream flow prediction. So a comparison between stream set and a raw satellite estimate image could illustrate whether the additional accounting for precipitation uncertainty can improve the stream flow prediction. We also try to investigate how the satellite precipitation ensemble performs compared to this forced by high-quality precipitation. All the simulations are conducted at hourly and 0.1 degree in our study watershed. So the hydrological model we used here is of hydro. Okay, now this slide try to summarize the performance of our proposed stream set precipitation ensemble and other global precipitation benchmarks. So first, as we can see in this upper finger. So since our ensemble is kind of different realizations, so we use this blue shadow to represent the ensemble spread. We can see the observation, which is a red line, is captured by the precipitation ensemble we created. However, the raw satellite estimate is black line, the image, is kind of far away from the ground-based precipitation measurement. Secondly, to make a comparable comparison between precipitation ensemble and deterministic precipitation data, we use the index, which is called a continuously ranked probability score, CRPS. So CRPS generally measure distance between one deterministic value and a distribution. So when the ensemble member is reduced to 1, CRPS will be equivalent to mean absolute error, MAE. So in this figure, we kind of calculate CRPS for precipitation ensemble stream set and MAE for all other deterministic precipitation data set. So it's purple bar here is the performance of the stream set. The lower the CRPS or MAE means a better performance. So this yellow bar is from the EI5, which is another widely used reanalysis precipitation data to trace the hydrological models. So EI5 here we can say it's kind of perform a little bit worse than the stream set. Its blue bar is a MassWeb, which is a merged data set combining satellite reanalysis and ground-based radar. So it's kind of one of the best precipitation data, has the best accuracy. So, but due to it need to include different measurement information, so it tends to has a longer time latency. But compare the MassWeb with our stream set, we can see a kind of comparable performance between stream set and the MassWeb. So now we are looking at the hydrograph predicted by the different precipitation. Notice that even if we use deterministic precipitation, we will also generate a stream flow ensemble because we consider the hydrological modeling uncertainty. So for example, if we use the ground truth image as the precipitation enforcement data, this stream flow ensemble spread will represent the uncertainty from the hydrological modeling process. But if we use stream set as the precipitation enforcement, the stream flow spread will convey the uncertainty both from the precipitation uncertainty and from the hydrologic modeling uncertainty. So basically, you can say that the stream flow ensemble predicted by a stream set has a wider distribution. And also it's kind of closer to the observed stream flow compared to the emerge. Because emerge itself has a lot of high bias. So the stream flow prediction driven by emerge also you can say has a lot of O estimate in its time series. We use KGE to evaluate the accuracy of this hydrologic of the stream flow time series. So the best value for KGE is 1. We can say the stream flow driven by ground truth precipitation has a best KGE value, which is reasonable. The stream set 1 kind of has a relatively lower performance than that from driven by ground truth, but it's still a better performance compared to the stream flow driven by emerge. So here we kind of conclude that by doing the satellite precipitation uncertainty quantification, we can for sure to generate a more reliable and more accurate stream flow prediction. Okay, let's see some take-home message. First of all, we use an ensemble to quantify the satellite precipitation uncertainty, and then we demonstrate how this satellite precipitation uncertainty quantification will benefit the stream flow prediction. So thank you all for listening. I will stop here, and I'm happy to take any questions.
Great. Thanks so much, Kaidi. Just a reminder, if anybody has any questions, feel free to just leave them in the chat, and we'll have a discussion session for all of the presentations at the end. So now we're going to move on to Dr. Fraser King. Dr. King's a machine learning and remote sensing scientist with PhD from the University of Waterloo, specializing in snowfall predictions, statistical modeling, and deep learning. He currently works at the University of Michigan as a research fellow, focusing on generative in-painting models for radar applications and unsupervised learning of hydrometeor microphysical applications or observations. His research interests also include enhanced modeling and model interpretability to improve the transparency and reliability of AI-driven precipitation models. So Fraser, whenever you're ready, go ahead.
All right. Hello, everybody. We're going to conclude today with a discussion on another type of precip. We're going to be looking at snowfall now. The good news is some of the images and figures that I've got in here have already been brought up by the previous talks, which were excellent. So that'll help us move along here. But yeah, we're going to shift gears a little bit and think about snow. So snow. This is snow laughing matter. I promise there's no more puns. I've already put 2 puns in 2 slides, and I feel like that's enough. But snow is very important for many reasons, right? Outside of the big impacts to global water and energy budgets through things like snow albedo feedbacks, that sort of thing. Maybe thinking a little closer to home, impacts to outdoor recreation, right? The skiing industry, sort of the finances around that rely very heavily on how much snow is falling from year to year. Thinking about things like surface hydrology, right, and disaster management. If you've got a lot more snow sitting in an area than you typically would, and that all melts out very quickly in the spring freshet, you could have issues with flooding, right, which can cause lots and lots of damage, and is a huge issue, especially where I'm from in southern Ontario. Snow removal or the non-removal of snow can be expensive if you go too far in either direction, right? And then obviously thinking about things like ecological impacts, if you have changing rain on snow events, that sort of thing, you can damage wildlife, prevent certain biological activities, eating, disrupting food chains, that sort of thing can cause lots of damages there as well. So snow has lots of impacts, very important. But it's very challenging to measure. This was one of the figures we'd seen earlier, right? Atmospheric microphysics is very challenging for all sorts of reasons. You can see the complexity, and this is an oversimplification of what's happening over very small regions of the atmosphere, right? And so with so many particles moving around and condensing, there's riming, vapor deposition, they freeze, they melt, they refreeze, they break up, right? This is a very difficult problem. And so it's often handled with parameterizations in models, and these have uncertainties and biases. which has downstream effects on your accuracy of your models. And so observational gaps in these different processes are really important to understand and very challenging to sort of reduce. Okay, so let's talk a little bit about snow particle formations. Some people may have seen this diagram before. It's called the Nakai diagram. It's been around for a long time, almost about 100 years now. But a researcher from Japan figured out this relationship for how snow particles, snow crystals, snowflakes form, related primarily to things like temperature and supersaturation, or the amount of moisture, humidity in the air. And so you have this curve as you go from left to right, from 0 degrees, down to -35, so colder on the right, and more saturation as you go up. Where you get different dendritic formations in this first region, right? You can have needles or columns in the middle, more dendritic growth sort of between -10 and -20, and then back to plates on the right-hand side. And so this is a really interesting relationship and can result in all sorts of different formations here. One really cool observation that I found, and I've linked to this down below, was from Matthew Sturm just a couple of years ago, where he was sitting on his deck in Fairbanks, Alaska. And he noticed as he was sitting there, all these different types of snowflakes forming, over a very short period of time. And when he looked at these, you had this evolution from these dendritic snowflakes to these thin plates to hollow crystals and to these needles as the temperature changed throughout the day. And so this is, I think, a really interesting and challenging thing about snow is it changes so much over, these particles change so much in shape, size, density over such small periods, which makes modeling it very, very difficult. I've got a few animations here. This is from Dr. Ken Librick at Caltech. He's got these amazing lab-grown experimental setups where he grows ice crystals under different conditions. You can see these dendritic flakes forming here, right? You can see these ones grow in different shapes and directions as they pulled in all that moisture surrounding them. I would highly recommend checking out some of his publications and the images that he makes, as they're quite beautiful. And the way he does this, he calls these designer snowflakes. And so these are different than what you would typically see, out in the real world, as those snowflakes are falling, right? They're melting and evaporating, they're refreezing, they're colliding into each other and breaking apart. So they don't typically look this pristine. But he uses this, seed crystal chamber and a camera, and he can control sort of that supersaturation value we looked at earlier and the temperature to almost draw these like an Etch-a-Sketch, which is kind of neat. He can make his own ice crystals. And another cool fact is he was actually one of the design consultants for the snowflakes used in Frozen. So that was kind of neat. I guess you want those to look realistic. But this raises a question. Many people have heard, are snowflakes all created equally? Are they all unique? Well, again, out in the real world, we've got all these different conditions and microphysical properties changing constantly. They do typically look unique. But when you're growing it in the laboratory, you can create these twin snowflakes, which is really cool. And I'll show a short video here where, again, if you've got the exact same sort of environmental characteristics across a very short area, you can regrow nearly identical snowflakes, which is pretty cool. But yeah, in the real world, they're oftentimes not, they don't look that pristine. They're very complex. Some people, I think the number of different types of snowflakes that exist out there, up to 100 now, some researchers have. I think Dr. Ken Librick has it down to around 33 or so. He's broken them down into, and here's an exercise I'll leave for people afterwards. Try to match the photos to the classifications here, right? There's many different shapes, and they all change depending on these atmospheric conditions, from bullets to capped flakes to dendritic ones to very rimed particles as they fall through super cooled liquid water, that sort of thing, which just adds additional complexity for us modelers when we're trying to think about snowflakes. Okay, so that's a bit of background on snow. How do we actually measure it? Well, here's a picture of me out in the field. You don't want to do it this way. Measuring it by hand and counting them doesn't do a very good job. So don't do that. Typically, what we've got are different, automated instruments out there. So these could be things like GNR or pluvio gauges. I've got an image of one of these here, which are shielded with these windshields. And they collect snowflakes that fall in. You can kind of measure differences in the weight from when they melt to get an idea of how much snow is falling. But these are expensive, right? And they take time to set up and maintain. So in remote areas where we have a lot of snow falling, we often have these huge observational gaps, right? Where we don't really know what's going on in between them. And this is where we rely on what I was talking about earlier, these different numerical models, reanalysis products, those sort of things to try to fill in those observational gaps. And so these are great, very powerful, oftentimes do a good job. But when you get to these really poorly constrained regions, for instance, like the Canadian Arctic, there's lots of uncertainties between these sites, right? Huge gaps of hundreds and hundreds of kilometers. So typically what a lot of our work has been focused on, during my PhD and, thinking beyond now into my postdoc is how we can use satellites. And we saw in the previous talk an excellent demonstration of, satellites like GPM. We've done a lot with CloudSat, another similar satellite, which can use their different radar instruments to sort of peer inside of clouds to understand how much snow is falling in that cloud and how that kind of relates down to the surface snowfall rates. And just as a brief overview of how that works, right? If we have an overview of CloudSat, say marked in red here, as it's passing around on a granule, it's a nadir, so it shoots its active radar beam down, peers inside clouds, reflects off the hydrometeors within, and we get these different, properties. We can see reflectivity profiles in that top panel, snowfall rates in the middle, or extrapolate those down to surface snow accumulation estimates or snowfall rates, which is very powerful over these remote regions, right? As these are some of the only observation-based sources of information that we have available to us. Now, of course, CloudSat is around no longer, did a great job. That's why I had a tombstone next to its name on the previous slide. But we have other satellites out there. GPM, as we saw in the previous talk, very powerful and can be used in some cases for snow, as we've seen. But thinking forward to the next generation of satellites like EarthCare and whatever AOS looks like down the road, we're going to continue this observational process of collecting snowfall estimates from these remote regions with future missions, which is very exciting. So keep your eyes peeled for those in the coming years. However, one problem with this, many microphysical assumptions, right, about what these particles look like. How do you relate that reflectivity information to a snowfall rate is very challenging. As we saw, these snowflakes come in many different shapes, sizes, densities, right? That all adds additional uncertainty. And so I just want to talk briefly about some of the things we've been doing to understand these processes at the University of Michigan by thinking about another type of surface instrument. This is the Precipitation Imaging Package, or you'll see it called the PIP. It's a distrometer, which is just a fancy way of saying it's a video camera, as you can see in panel A, pointed at in this case, 150 watt halogen bulb. And as particles fall sort of between the bulb and the camera, we get the silhouette, as you can see in the video on the right there. There's many more videos uploaded here, so check this out on YouTube if you get a chance. This one was on Christmas Eve, which was kind of fun. But you can see as the particles fall, we can capture this information to learn things about the particle size distributions, their densities, their fall speeds, what the liquid equivalent water would be, all from these high resolution images. So these are the sort of the microphysical properties that we need to help enhance those retrievals from things like satellites, as we were seeing. And so one thing we've been doing recently is putting a huge data set together. A lot of these problems come back to the data you have, right? So if you have bad data to train your models, whether that's a machine learning model, some sort of empirical numerical model, you're probably going to get bad outputs. So we put a lot of work into creating this microphysical repository online here on the UM's Deep Blue Data Repository. So just trying to promote that and say if people are interested to check that out, because we've got data from a whole bunch of sites. In fact, we've got data from 10 different locations over about 10 different years. Many of these are GPM ground validation sites from many different countries, ICEPOP in Korea, ICP, Olympics off the coast of Kaunas, GCPEX in Canada. Really a multinational approach or an international approach to gathering snowfall from many different regimes, which is quite important as you want to capture all these different processes as different regional climates will experience different types of snowfall more frequently, which is very important if you're trying to create a robust model. So we've made this available and we've done some early analysis on what these distributions of different snow processes look like at these different sites, looking at things like the numbers of particles, right, what their densities are, their fall speeds, that sort of thing. And just to summarize what that looks like, we've used a couple different approaches. Principal component analysis, PCA, many of you might have heard before, allows us to kind of look at underlying embeddings or dimensions, underlying features really in the data. So instead of just looking at the raw density values or fall speeds, what is kind of underpinning all of these processes. And so one of our studies, which is in review right now, looked at this using PCA and was able to break snow processes up from these different sites into these 6 different groups, from very wet and dense snowfall, right? More on that side of the hail we saw earlier in that earlier talk, compared to cold and dry, very light, fluffy snowflakes that you might be familiar with, the really pretty, pristine dendrites, for instance. Deep and shallow systems, that sort of thing. We found we were able to sort of break them up into these process groups, which was quite interesting. And we've taken that one step further to look at nonlinear groups as well more recently, nonlinear dimensionality reduction techniques to break these processes up further, and to look at rain, mixed phase precipitation, and snow. So really everything we've been looking at here today, to see how these different groups break up, and how the particles evolve over time between these groups, across all these different sites that we looked at. And so we're finding these really interesting pathways that particles typically take as they go from, for instance, a rainy particle to a partially frozen mixed phase particle, and then, a more frozen, pristine ice particle, depending on how your atmospheric conditions, right, in terms of temperature, humidity, that sort of thing, change throughout the day. So in summary, snow is very complex, right? Lots of different shapes, sizes, densities, lots to account for, and many open questions about how to relate information, in the atmosphere to those surface processes, as these particles fall and evolve, right? Good data sets are often very challenging to obtain, but are extremely important, right? These are usually in cold, remote regions, so it's tricky to go install and maintain instruments there on the surface. And so we've really put a lot of work into, creating these robust data sets, making those available to other researchers to help facilitate future snow research, as we believe these are really important for, enhancing numerical models, and, future and current spaceborne retrievals of snowfall. This will be, again, tying back to that motivation, really useful information for preparing for future changes in precipitation patterns as our global temperatures continue to rise. And so just to finally conclude, I want to highlight a few conferences and groups of people who are interested in learning more about snow. The Eastern Snow Conference is a great one here in Canada and the US, for talking specifically about snow processes. IPWG is also an excellent smaller workshop looking at different precip products, and that includes snow, obviously, here. And then, of course, as the host of this talk today, AGU's Precipitation Technical Committee is a great source of information to learn more on these topics. And so, yeah, snow, I always say snow is very cool. I think it's a cool research topic. You get these really cool shapes. And if anybody has any questions on my talk, or I guess any of the other talks today, we'd be happy to take those in the last few minutes that we have here today. Thank you.
Thank you. So we have a couple of minutes for a couple of questions for any of our speakers. So if you feel comfortable, unmute and ask, or you can drop something in the chat. So in the chat, we have a question for Kaidi. It seems that MSWEP performs pretty good in uncertainty analysis. Have you checked the performance in streamflow simulations compared to iMerge or your stream data?
No, we didn't do that. So, cause our study area in the class area, so we use the AORC data as the best precipitation benchmarks to make comparison with iMerge stream.
Great. I think that there were 2 questions related to Holly's talk that were from earlier. Do you want to respond to those, Holly?
Yes. So on the first question was asking about generally if it's possible that deforestation or land use change might affect hail sizes, hailstorms. It's possible that the change in land use could influence more of like the boundary layer temperature and moisture profile, which might in turn influence the storm characteristics and therefore hail. I think there need to be a bit more work done to understand the correlation between those specific changes in hail. So it's difficult to conclusively say if there's a direct link there. And then the other question about, is it possible to estimate masses of hail from radar or satellite data and how accurate that is? Yes, it is possible to estimate hail sizes and mass from say like radar and satellite data, one of the tricky things with hail, so I'll take an example from like snowstorms, for instance. So in some field campaigns with snow, there's ground-based radars, which are scanning and looking at the storm. And you can have planes that are outfitted with instruments that can record like snowflake size or ice distribution and get those really nice particle images like Fraser was showing, as well as like measure ice water content that are flying directly in the storms. So you can compare what the ice mass and the size distribution is where the radar and the plane are kind of hitting the same grid point essentially. With hail, we cannot fly planes really through the actual storm itself. And so we're a little bit more limited in how we're able to do that. You could, for instance, just take like the lowest level radar scan and assume like very little melting or something and try and get data that way. But then that's also reliant on needing like a accurate hail report or size at the ground, which is actually not super common. So it's we could do better on that if we want to try and improve that.
Great. So there is a question, Kaidi, for you in the chat, but I would like to ask Fraser a question, so that way everyone gets a way to ask something. Kaidi, just go ahead and respond to that in the chat itself. So Fraser, I really liked your talk about snow and how it just seems really uncertain in the largest idea. What do you think is the most important thing moving forward for like snow science in terms of, should it be better data quality? Should it be more clarity in different methods that are used by different groups to be able to quantify things within snow uncertainty? What is your thoughts on where the science should go?
Sure. Yeah, that's a tricky question. I think my biggest point probably would be thinking about the data. I think a lot of the models that we make, I've done a lot of machine learning modeling, which is, empirical and statistical modeling based on, whatever data you feed into it is going to be really important for impacting what the model provides. And so if we don't have a good, robust set of observations that really captures the comprehensive nature of these different snow proces at different locations, if you train a model, at site A, it's not necessarily going to do a good job and generalize to site B, which I think is sort of the biggest problem that I've seen in a lot of these, recent models that have come out. So if we can, put together, and that's why we have this data set that we put together, the more comprehensive and high quality observations we can get of all these different processes, I think will really facilitate an improved understanding, and you can develop more complex deep learning models, for instance, from that data set. So I think that's probably one of the biggest challenges, is just collecting those from all the sites. They're very expensive to collect and then standardize, but if we can do that and really improve that in the future, I think that would be a big boon for the science.
Awesome. Thank you so much. So we are at time. I would like to thank all of our speakers once again. I have a quick announcement to make. That I would invite any students or anyone who is working with students to have those students who are going to be presenting at AGU sign up for our AGU Technical Committee's award. We give out a cash award to 5 students, and then they also are featured in our first 2 seminars every year. So this is a different sort of award from anything that is ran by the outstanding student presentations that happen at AGU. So it's a separate thing. Please apply for it if you're a student, or tell everyone. We want more people to do it. You can find it on our website. So thank you once again to our speakers. This was a wonderful hour. I had so much fun. And have a great day, everyone.
Thank you all.
Thanks, everyone.